Welcome back, chemistry fans. What we're going to do next is the Unit 9 exam for the dual enrollment. This is the heat unit. So let's jump into it and let's see about solving some problems. Figuring out what you did wrong, again, is the most important part of it. The answer, I'm not so interested in. I need you to prove to me that you understand the concept. So please don't focus on the numbers. That's not where the problem is. You got to tell me how you got to those answers. All right, so let's do this. Number one, we've got two substances. One of them has a higher specific heat than the other. A is 1.83, B is 0.91. Now, the first question is, though, which is the better insulator? The better insulator is the material that has the higher specific heat. That is true. Just like water has a higher insulation specific heat, 4.18, than does a metal of a 0.98 for aluminum or something along those lines. So this is the key. But another way to think of this is what causes the different specific heat values. And it says that you must address the molecular structures. And so any mention whatsoever, I was very, very satisfied with it. But bottom line is it ends up that there are different structures. And if you have a molecule that allows heat to escape through it, well, then it is going to have a lower specific heat because it can take this path from one atom to the next, and it can continue on. But if we have something like waters, if we have something like a more complex molecule where the structure happens to trap the molecules, well, I'm sorry, so this one should all be a linear thing. But if we have something that causes the heat to get trapped inside, well, then that's how the insulation occurs, because this problem develops that the heat doesn't find a clear path to escape. Whereas when we have metals, again, it's a long chain, a network solid, and the heat can conduct quite easily through it. But whenever we have structures that are more complex, they tend to hold in their heat a little bit better. So any kind of representation with that will suffice to help understand or explain how you have different specific heats. Number two, what we've got here is a specific heat problem. Notice I only have one substance. One of the questions I always ask you is, how did you know which equation to use? Well, that's right here. But if you got this wrong, you clearly need to still tell me, why is this the correct one? And it's not because I gave it to you. You need to tell me that it's only one substance. It only has, it doesn't have a reaction involved. It doesn't have a heat of formation. It doesn't have multiple reactions. So what we've got is this single substance heat problem. So we're just going to simply substitute in these values, mass of 335, specific heat of 4.18. The change of temperature is what we're looking for. Now, it says that it is going to lose 9750. Many of you who missed this did not put the negative symbol in there. So that's probably where your answer went awry. 9750 divided by 335 divided by 4.18 gives us a change of temperature that is negative 6.96. Now we have the initial temperature of 65. So I've got 6.96 negative equals temperature final minus 65.6. So what I'm going to do is I'm going to add 65.5. I said 65.5 to both sides. And what you end up with, 65.5 minus 6.96, you get a final temperature of 58.5. 58.5 positive is what you get. All right, number 3. Now this one, it is two substances. So what we need to understand is that heat in, oh, sorry, this is not, sorry. So what we've got here is we are simply solving for the specific heat. So again, a single substance, not two substances, not a heat of reaction, not multiple reactions. So we've got first to convert 2.3 ounces into grams. So that means setting up some kind of dimensional analysis, grams per ounce equals however many grams over to 2.3 ounces. And so we can cross multiply 2.28.35 times 2.3, and you would get 65.205 for the grams. So that's where we will start with our equation. That's our mass. Our specific heat is what we're looking for. The change of temperature, it says it quickly converted to, it was observed to be that, and then it quickly converted. So our final temperature is 23.1. Our initial temperature is 6.6 negative. So that means I'm adding it. And the amount of heat it absorbs, 0.252. Now that's in kilojoules, so this needs to be in joules. So that makes that one multiplied by 1,000. So that is going to make it 252 joules. So we could solve 65.205, I'm sorry, 252 divided by 65.205 divided by 23.1 plus 6.6, and you get specific heat of 0.13 joules per gram degrees Celsius. All right, number three. Number three is done. Let's go to number 4. Number 4 is where we have two substances. We have a liquid in a refrigerator. We have a liquid that is on a shelf, and we are going to mix them together. So we are going to take the mass. Oh, so and so what we have, the an N is going to be the alcohol, and the out is going to be the mixture, the fruit stuff. It's going to lose heat because, I'm sorry, got that reversed. The alcohol is going to lose heat because it is hotter than the mix that is coming out of the refrigerator. It's going to gain heat. All right. So let's see if we can sort out all the information. Water-based solution in an adult beverage mix after 56.6 grams of a 15.9 degree ethanol was added. So that's the initial temperature. So that's subtracting 15.9. We don't know the final temperature here. It does say the specific heat of ethanol is 2.53. And because it's losing, all of this is going to be a negative heat. There's going to be 256.1 grams of the water-based solution before combining to the water solution and the 56 grams. The solution is taken from the refrigerator, and it is a water-based solution, so we're just going to assume that its specific heat is 4.18. And we are going to take the final temperature. We don't know, but we do know the initial temperature is 5.1 degrees. Okay. So we've got all of our information here. So now we just got to solve for that final temperature. And this is a very long algebra problem. 256.1 times 4.18 equals 1070.5 times TF minus 5.1. That is equal to 56.6 times 2.53, a negative 143.2 times TF minus 15.9. All right, so we continue on. We got to distribute now these values into the temperature ranges. So 1070.5 TF minus 5,459.6 equals negative 143.2 TF plus 2276.9. All right. Now let's bring the TFs together. So I'm going to have 1070.5 plus 143.2. And so I'm going to have 1213.7 TF is equal to, I will bring the non heat values together, the non-temperature values that are whole numbers or that are just integers. They don't have coefficients attached to them. I'll bring those together next. Okay, so now I've got 5,459.6 plus 2,276.9, and you get 7,736.5. We're going to divide both sides by 1213.7, and you end up, your final temperature is 6.37, somewhere in that neighborhood. Okay. So that's how much it came down. So it didn't raise the temperature a whole lot, but the temperature of the ethanol did come down quite a bit, but they both met somewhere in the middle. All right. Number 5 is a Hess's law problem. And what we have for Hess's law is we got to try and make everything equal what we see down here in the total reaction. Well, the first thing we should notice is that the ethanol is on the wrong side. So I'm going to have to flip that and make that into a positive 8750. So now first reaction is perfect because now I have something in both sides that is correct. I will now notice that my H2 needs to be multiplied by 2, meaning that I need to multiply my heat by 2. Now that is correct. Same thing for my second reaction. My carbons need to be multiplied by 2. So now all we got to do is just simply add all these together. So I got 875 minus 394.51 times 2 minus 285.8 times 2. And you come up with negative 485.6. See, is that the end of that page? That is the end of that page. So now let's jump to question number 6. Prove that this is endothermic or exothermic. If it is, on the left side, those are heat values that you need to add. Anytime you add energy, that means it is endothermic. Number 7. Prove that it is absorbing or giving off heat. This is a separate statement. Anytime you have a negative, that is indicative of exothermic. Exothermic means that you are giving off heat. Number 8. Now on this one, we do have a heat of formation table. That tells you that you must use products minus reactants. It is given to you. There is not a single substance. It is a reaction. It's not multiple reactions. So we know it's not a Hess's law problem. These are the statements that you must make, or I will ask you to make these statements, not because I give it to you. You must know when to use which equation. So products minus reactants. All right, so we're going to go and find the first product of CO2. And let's see, it's right down here. It's a negative 393.509. But there are 4 of them, so that needs to be multiplied by 4. There are 6 of the waters that are liquids. So I'm going to go find my waters and make them sure that they are liquids. And that is 285 negative 0.83. 285.83. Now minus the reactants. All elements that are by themselves are 0. So you won't find it on the chart. Now we're going to go and find C2H6, and it is a negative 84.68. But because it is minus that value, it is going to be times a negative 2. So that made it into a positive. So now we just add all these values together. 393.509 times 4 minus 6 times 285.83 plus 2 times 84.68. So this answer will end up being negative, a negative 3,119.6. And if you're using sig figs, well, I guess it has to be 1, 2, 3, 4. So it'd be somewhere in the 3,120 range. Negative, I'm sure, is probably what that is. All right, let's see. What do we got next? So that takes care of this page. Let's jump into question number 9, I believe, next. In question number 9, you are given a mole map. And so how do we know what we're doing here? Well, it's asking you for how much energy given a heat of formation. So it's not products minus reactants. I didn't give you the table. It's not a single substance. It's not a multiple reaction. This is a heat of reaction. And so we are going to have to figure out how much of this is accurate. Because if I have only 1 mole, or if I have 2 moles of this, rather, this is how much it will make. But I'm given 28 grams. So we need to figure out, well, what does that have to do? How much does that actually give us? Is that 2 moles? So we're going to have to add it together. So H plus F equals 20. Well, that's just a little bit less than what we're going to be ending with. So look at your mole map. So you're going to start with 20. You're going to go into moles. That means you're dividing by this weight. So 20 divided by 28 means that we are only using 0.71 moles. Well, that's far shy of the 2 moles that we need to make 537. So what we're then going to do is we're going to multiply by that heat of formation. So I'm going to take 0.71 and multiply it by 537. And this is a negative because it is exothermic. So 0.71 times 537 gives me negative 381.27. And again, with sig figs, it'd be negative 381. All right, number 14. What is the condensing point? Solid, liquid, gas on this chart. This is melting and freezing. This is condensing. This is evaporating. So it needs to be somewhere in here. To me, that looks exactly at 75 degrees. If you put 55 degrees, that's too low. If you put 95 degrees, that's too high. But there's somewhere in there that there was a range of answers that were correct, and you just need to eyeball that one to get pretty close. All right, so I've got one more page to do with you. Let's get into number 15. At which temperature can liquid exist? Or what is the hottest temperature at which liquid can exist? The hottest temperature you needed to be able to pinpoint is B. This is your triple point. This is solid, liquid, and gas. Melting and freezing occurs on this line, evaporation, condensing, sublimation, deposition. B is your critical point that you should have been able to identify. All right, now we have spontaneity. The formula for spontaneity in this case is delta G equals H minus TS. So what we've got to do here is we've got to calculate what that value is. You are given H as negative 120. You are given the temperature change. You're given the temperature this is occurring is 290, but because of the minus sign, it's negative 290. The S value is minus 150, but this is in joules. So we need to divide that by 1,000 to turn that into a kilojoule because our answer must be in kilojoules. It must match. So I've got 290 times 150 divided by 1,000, and those are both negative, so that's a positive. So minus 120 gives us a negative 76.5 kilojoules. That is our value for this heat. I'm sorry, for this spontaneity. This is the Gibbs free energy. Now, is it endothermic or exothermic? The heat tells you that it is negative. It is exothermic. Is it endergonic or exergonic? Again, the negative symbol that we just calculated tells you that it is exergonic. Okay, this is everything that I hope that you would have demonstrated mastery of. If not, you will have to start trying to do that for me. Thank you very much. Take care. Bye-bye.